So, remember that we have done improper integrals in the previous class we have started. So, today we shall continue from that only. So, recall that we have started these improper integrals, and I have told you earlier that what kind of integrals are called improper integrals. So, that basically there are two kind of improper integrals, that one is type 1 improper integral and the other one is type 2 improper integral. So, type 1 improper integral, just you recall that type 1 improper integrals, they are of the form, just you recall that it is integral a to infinity f x dx, integral minus infinity to b f x dx, and that may be of the form minus infinity to infinity f x dx, where this function f should be bounded on this interval, on the given interval of these limits. And also we have discussed about convergence, the definition of convergence of these improper integrals, that we have discussed in the previous class. We have given we have seen the definition of convergence of these improper integrals. So, I am not going to repeat that, the convergence definition of these improper integrals, and then you remember that this type 2 improper integrals are of the form that integral a to b f x dx, where a and b they are finite, a b finite, but the function f is unbounded at finite number of points of this interval a b, but f is unbounded at finite number of points in this closed interval a b, that the function may be unbounded at these endpoints also, at a or at b. And also I have given in the previous class that definition of convergence of such kind of the type 2 improper integrals also. So, today actually we shall discuss basically some other kind of test of convergence of improper integrals. Well, just you recall that definition of this kind of improper integrals that we have given. From that definition we can test that the convergence of the function, as well as we do find the, if it is convergent, then the value of these kind of improper integrals. But it may not be possible all the time that finding exact value of an improper integral by this direct method, even if that improper integral is convergent. So, we discuss about convergence or divergence of improper integrals through some test, that we compare with some known improper integrals, that the improper integral, if we know that it is convergent or divergent, then with that improper integral, we can compare some other improper integrals and get information about the convergence or divergence of that new improper integral. So, there are some kind of tests. So, today basically we shall discuss these some kind of test for convergence of improper integrals. Well, so some test of convergence of improper integrals. Today we are mainly interested on this test of convergence of improper integrals. Improper integrals. Well, there are several kind of tests. Here we shall discuss few of them. So, first of all that we discuss is this comparison test. First we shall discuss this comparison test. Well, in this comparison test, I mean if we are having a pair of functions, okay, first let us consider for this type 1 improper integral. Here suppose we are having two functions f and g, I mean they are like this, let f and g be bounded functions on this interval, say a infinity, with this condition that f and g they are also non-negative function, I mean f x is greater than equal to 0 and that is less than or equal to another that function g for all x in this interval a infinity. Then we can tell about convergence or divergence of certain kind of integrals, that then we get the following results. First one is, if I mean it is quite natural, because the function f is dominated by the function g. So, therefore, this is quite natural that if integral a to infinity g x dx is convergent, if this is convergent, then convergence of this integral a to infinity f x dx is assured, then this is convergent. Well, this is quite natural, that what we can expect here, that convergence of because this function f x is dominated by the function g x. So, convergence of the improper integral, that integral g x dx from a to infinity, if it is convergent, the convergent of this integral also assured. Similarly, that another natural thing that we can get is the following, that suppose I mean if the integral that integral a to infinity f x dx is divergent, if it is divergent, then the integral a to infinity g x dx is divergent. Well, so these two tests are called comparison test. One more test we will get, that is also kind of comparison test. Suppose I am having here if I mean in this case I am looking into a function h x that let h be a bounded function on this interval a to infinity. If this integral a to infinity absolute value of this function h x dx, if this is convergent, then we get that integral a to infinity h x dx is convergent. Well, in this case we also say that this integral converges absolutely also, because the absolute value of this function h x that is convergent. So, we also say that sometimes it is absolutely convergent. Well, I can give you few examples now to verify this test. So, look at this examples. Well, here we will consider some integrals and test their convergence. So, investigate the convergence of the following integrals, Here first one I am considering is integral 1 to infinity dx by x square 1 plus e to the power x. Then next I am considering that integral 1 to infinity x plus 1 divided by square root of x cube dx, and third one I am taking is that 1 to infinity sin x by x cube dx. Well, let us consider this A part. So, in this case we are having, I mean that function f x, suppose we take the given integrand of this integrand, let us consider that as f x, that is 1 upon x square 1 plus e to the power x, and here actually we shall apply that comparison test. So, for that we have to think of another function g x, and we shall do comparison with the given function. So, here just you observe one thing, how to get the other function g x, so that we can compare with this. Well, here this range of integration you just look at, it is from 1 to infinity, that is x is greater than or equal to 1. So, for x greater than or equal to 1, we can have that this integral 1 upon x square 1 plus e to the power x, I mean that will be strictly less than 1 upon x square, because of this value, that 1 plus e to the power x, that is always, that is I mean greater than 1. So, therefore, 1 upon this 1 plus e to the power x, that will be less than, I mean we can say that is less than 1, this portion, that 1 upon 1 plus e to the power x, look at this part, 1 upon 1 plus e to the power x. This portion is less than 1, strictly less than 1. Look at this factor, that 1 plus e to the power x. So, in this range, of course, we always get that for other values of x also, but here certainly we are having that 1 upon 1 plus e to the power x is, that is strictly less than 1, and therefore, we get this function is 1 by x square into 1 plus e to the power x, that is strictly less than 1 by x square. So, we shall consider this function 1 by x square is our function g x, because for this function g x, I mean, so therefore, we take that let g x be 1 by x square, because this function I mean looks somewhat better, I mean through our that definition of convergence of improper integral, that we can always verify this convergence of this improper integral, improper integral, that integration of g x dx, x varies from 1 to infinity in this range. I mean, this is somewhat simpler kind of function, or that we can evaluate this improper integral, or we will able to say the convergence of this improper integral through our that definition of convergence of improper integral that we have seen earlier. So, in other words, what I am saying is the following. Here we shall verify that the integral that g x dx from 1 to infinity, this range. Okay. So, I think we will be able to verify its convergence, that 1 to infinity. One thing you just notice, this function f x and g x, they are fulfilling that conditions of the comparison test we have seen. I mean this function f x is dominated by this function g x, and they are also non-negative on this interval 1 to infinity, okay, and they are also bounded in this interval. So, therefore, they fulfill all the criteria of that comparison test. Only thing remains is that checking the convergence of this improper integral. So, for that, you know, from our the definition of improper integral, that we can check its convergence. Well, for the convergence of this improper integral, we look at this limit 1 to b 1 upon x square dx b goes to infinity. So, we find out value of this, I mean integration, and then we take limit b goes to infinity. So, you know that if you do that integration, that limit b goes to infinity minus 1 by x, that in range is from 1 to b, okay, and after simplification this and taking limit b goes to infinity, we get this value is equal to 1. Therefore, this integration g x dx x from 1 to infinity is convergent. So, this integral 1 to infinity g x dx is convergent. So, by the comparison test, by comparison test, we get that the given integral in A, the given integral in A is convergent. Well, so similarly, let us solve that B part. I mean, we shall test the convergence of the improper integral given in B part. For that, okay, let us recall what was that integral in B part. It was integral from 1 to infinity x plus 1 divided by square root of this x cube dx. This was the integral given in the B part. Well, for this also we shall apply that comparison test. Just you look at one thing, that x plus this integrand you consider x plus 1 divided by square root of x cube. So, for this integrand, well, this is, we can get that this is always greater than that x divided by square root of this x cube. Okay. So, this is we are taking the positive square root, you just look at. So, therefore, if you break into two parts, this left hand side, that x divided by square root of x cube plus 1 upon something, 1 upon this square root of x cube. So, therefore, something positive we are getting here always, 1 upon square root of this x cube, we are taking this, I mean positive square root. So, therefore, we are getting that in the left hand side we are getting is this x divided by square root of x cube plus a positive quantity, plus a positive quantity. So, therefore, we can always get this inequality or this function. Here we shall consider f x is the function here given to us, okay, and that the other one here I will take this be say g x. Well, I think in our definition we had considered the other way around, I mean the notation. So, if you like you may interchange the notation, that you may consider that the function you can take here, that x plus 1 divided by square root of x cube, this you can take also g x, and the other one here in the right hand side, that also you may consider as f x. What is there in a name, I mean you may interchange the names also. Well, only thing is that we have to verify whether it is fulfilling the criteria of the comparison test 2, that second one. Well, for this, now we shall verify the convergence of this improper integral, that g x dx, I mean that is integral 1 to infinity x divided by square root of x cube dx. In fact, here we shall show that this improper integral is divergent. So, therefore, the given improper integral that is also be divergent according to our that comparison test 2. Well, then how to verify that it convergence or I mean divergence of this improper integral, that again we shall go to our definition of that meaning of convergence of this improper integral from that direct method. Well, you can verify that this g x I mean this g x is actually equal to that x divided by square root of x cube. Actually this is equal to 1 upon square root of x. So, therefore, we have to just consider this integral 1 to infinity 1 upon square root of x dx. Well, for the convergence of this improper integral, you can check that this limit b goes to infinity integral 1 to b 1 upon square root of x dx. So, you find the integration of this integration and then evaluate in this range 1 to b and take limit b goes to infinity, and obviously you will get that it is actually equal to infinity. Not difficult to check this one. So, therefore, the given integration is divergent from that comparison test. So, therefore, by the comparison test, the given integral that integral 1 to infinity x plus 1 divided by square root of x cube dx is divergent. Well, next we shall look at the third improper integral of this example. Recall that this third improper integral was like this: integral 1 to infinity sin x divided by x cube dx. So, for the convergence of this improper integral, we are considering that third comparison test, you can say the third bit of the comparison test I had written. Well, in this case, this integrand sin x by x cube, if we consider its absolute value of sin x, that is less than or equal to 1. So, therefore, we get that this is less than or equal to 1 upon this absolute value of x cube. Well, for this improper integral we consider now is that 1 upon absolute value of x cube dx, but here this x varies from 1 to infinity in this range. So, x is always positive, and hence we can write this improper integral as dx by x cube. So, now again by the direct method you can check that you can find out this improper integral is convergent by considering this limit b goes to infinity integral 1 to b dx by x cube. So, by direct method we can find the value of, this is 1 to b dx by x cube. So, by direct method that we can find value of this improper integral, and this is a finite number. You check that this is finite. Okay. So, you check that this is a finite number, and hence we get that the given improper integral is convergent. Hence, the integral 1 to infinity this sin x by x cube dx is convergent. So, this is how we apply comparison test, and we shall see more problems in tutorial class or in that assignment sheet. So, I have told you that today we shall discuss about that several kind of comparison, several kind of test for convergence. So, this comparison test is one of them. So, besides this comparison test, we are having several other kind of test of convergence. So, among them the other important one is the mu test. Next we shall consider the mu test for the convergence. Well, for this mu test for the convergence of improper integral, that here again we shall consider that type 1 improper integral. Well, in case of that comparison test, we had considered only the type 1. So, what would have been that similar kind of comparison test for type 2 improper integral? Well, just let me give little hint that it goes similar way, that for that comparison test for type 2 improper integral. So, for the convergence of type 2 integral, that comparison test, okay, let me write down this then the comparison test for type 2. Comparison test for type 2 improper integrals. Type 2 improper integrals. Well, for type 2 improper integral, we consider that again, suppose we are having two functions, that f and g, and f is dominated by the function g and this is, they are non-negative. Well, and suppose the functions f and g, they have point of discontinuity or unboundedness at the point A. So, the functions f x and g x are related like this, and f and g are here continuous in this interval that A B say, or f and g, they are both unbounded at this point A, okay, continuous in this interval A B, and both are unbounded at A. So, that similarly you write down this test, here we get is like this, that if integral from this improper integral a to b g x dx is convergent, similarly you write down then integral A to B f x dx is convergent, and if this integral A to B f x dx is divergent, then this integral A to B g x dx is divergent. Well, so similarly we can get comparison test for this type 2 improper integrals also. Next we shall consider that another important one that I have already told you, that is the mu test, that is very useful also, that mu test. Well, this mu test is basically, this mu will be a real number, and depending on that mu, this real number mu, we get the convergence or divergence of improper integral. So, let us consider that conditions, that what conditions we impose, I mean, or we consider, so that it will convergence or divergence. So, again here first we shall look at this type 1 improper integral. In this case we consider that let f be a, as before, that bounded function on this interval a infinity, and of course we consider here that a is greater than 0. Okay, a is greater than 0. Look at this interval we are considering, a to infinity, a greater than 0. So, here first condition we get that if there exists a real number mu, mu is a real number with mu greater than 1, such that we have this condition that limit x to the power mu multiplied by this function f x. We test this limit x goes to infinity. We multiply this factor x to the power mu with the function, given function f x, and we check the value of this limit. If this limit exists finitely, means it exists and it is a finite value, this exists finitely means exists and a finite number. Okay. Then we can get the convergence of the improper integral, integral a to infinity f x dx is convergent, or this converges. So, for convergence of this improper integral a to f x dx, we just verify this limit, whether this limit exists and that is a finite real number or not. Well, similarly here of course you recall that this mu is greater than 1, I mean this criteria also it should satisfy. We should not ignore this criteria that mu is greater than 1, this is very important. If mu is less than or equal to 1, then we will not have this kind of scenario. In that case we get the other result, that if there exists a real number mu less than 1, Okay. Remember that here we are considering this real number mu is less than or equal to 1, and in this case if the limit x goes to infinity x to the power mu f x, if this exists finitely and should not be equal to 0, if this exists finitely and different from 0, and different from 0. This is also important, you should keep in mind. Then this improper integral diverges, that a to infinity f x dx, this is divergent, then this diverges. So, in this first case actually we are testing the convergence of this improper integral. For this we should able to get a real number mu that is greater than 1, and this limit should also exist finitely, then we can get in this case, in this circumstance. Okay. And for this second case, here this mu is less than, here we are testing, in second case basically we are testing the divergence of this improper integral, and for that we need to have this kind of circumstance, that mu we should get a real number less than or equal to 1, and this limiting value that should exist finitely, and also this is different from 0, then we get the divergence of this improper integral. Well, this is about our type 1 improper integral. So, similarly, we are also having mu test for type 2 improper integral. So, for that also similar kind of results are there, and those results are like this. Here we consider that f is in this type 2, here we will consider this type 2 improper integral, and you know that for this type 2 improper integral we consider this closed interval a and b are finite numbers. So, here we look at the case that f is unbounded only at a. Okay. So, let f be unbounded only at this a. So, in this case mu test will be like this. First we shall consider that convergence of the improper integral from a to b, integral a to b f x dx. So, for that convergence what situation we should have, or what should be this real number and what limit you are going to test are like this. If there exists a real number mu, of course, here this mu is greater than 0 and less than 1, such that limit x tends to a, x minus a whole to the power mu here, because the function is unbounded only at a, that is why we are considering this factor x minus a whole to the power mu and this multiplied by f x. We have to consider this limiting value of the product x minus a whole to the power mu f x. If this exists finitely, then this integral a to b f x dx this is convergence, this converges. And second case, there similarly we get divergence of the improper integral if it satisfies the following. If there exists a real number mu that is greater than or equal to 1 such that this limiting value that x tends to a, x minus a whole to the power mu, same limit here we are considering, that same limit we are considering here. This exists, this integral this limit exists finitely and different from 0, exists finitely and different from 0, then the integral a to b f x dx is divergent, then this is divergent. Well, this is about type 2 improper integral and where the function f is unbounded only at this lower limit. Similarly, we get also that mu test for improper integral where the function will be unbounded only at b. So, in that case, if the function is unbounded only at b, then what are the changes we are going to have for this, I mean conditions we have written here for both these conditions, first and second, for both the conditions, what changes we have to make? Well, for that the changes we have are the following. I mean here that is what I have. I mean looking into this, that suppose here the function f is, here f is unbounded only at b, then the changes we are going to make here, okay, all these things are same, only change we will get is that this limit, obviously that x should be that tending to b, x tends to b, and this factor we are looking into, that x minus a, just you look at x is here bigger than a, greater than a, x is greater than a in this case. So, therefore, this factor we should consider as that is not x minus b, because x will be smaller than b. So, therefore, this factor we shall change into b minus x. So, the changes in this case, all these conditions that mu test, the criteria for mu test are same, except, so in this case here all these criteria are same, we make the only changes, the changes we make in the above test, are x tends to b and this x minus a whole to the power mu, this factor will be that x minus a whole to the power mu is replaced by this b minus x whole to the power mu, and all other conditions are same. Everything is same except these two. X tends to A should be x tends to B, and this factor x minus A whole to the power mu, that we replace by B minus x whole to the power mu. This is what the change we have to do. Well, so these are mu test for convergence of improper integral. So, let us have an example how to apply this mu test. Well, so for this, okay, we can consider that suppose I will ask you to test the convergence of improper integral 0 to 1 dx divided by square root of x into 1 minus x. So, this is a type 2 improper integral. Well, this is one example of a type 2 improper integral, and in this type 2 improper integral, look at the integrand is unbounded at both the ends of these limits of integration. So, this is unbounded at x equal to 0 as well as unbounded at x is equal to 1. So, you know that such kind of improper integrals they converge if we look at two improper integrals we break, because this integrand is unbounded at both the ends. So, therefore, we break this improper integral into two improper integrals that we consider a number c in between 0 and 1, and we will look at improper integral. One improper integral will be from 0 to c and the other one will be from c to 1, and both are improper integrals, and we test the convergence of both those improper integrals, and the given integral will be convergent if and only if those two improper integrals are convergent. So, therefore, look at this. Here we consider therefore that some c, let c be a number lying in this interval 0 and 1, and consider these two improper integrals, that let I1 be the improper integral that from 0 to c, and that f x dx, f x is this given function, and I2 be the other one, that is c to 1 dx divided by square root of x into 1 minus x. So, now we shall verify the convergence of these two improper integrals. The given integral will be convergent if and only both these integrals I1 and I2 they are convergent. So, individually we shall verify the convergence of the improper integrals I1 and I2. For this, let us consider the first one, that is I1. Well, for this, now you consider this I1. Well, here we shall apply that mu test for the convergence of this improper integral I1, and here the integrand is here the integrand is f x is equal to 1 upon square root of x into 1 minus x. This is what the integrand is that. So, what values of that mu we consider and multiply the factor x to the power mu, so that the limit of, here you look at in this improper integral I1 in this interval 0 to c, the integrand is unbounded only at this lower limit 0. So, therefore, we have to consider this limit. Here I'll take this mu is equal to half, and then I'll consider that limit x tends to 0, that is lower limit, the function is unbounded at this lower limit 0. So, therefore, we have to consider this limit x tends to 0, x minus 0, that mu value I have taken half, and this function 1 upon square root of x into 1 minus x. So, this you can write down as limit x tends to 0, that square root of x, and that this is multiplied by the integrand x into 1 minus x, this whole square root, and that we are getting after cancellation of this square root of x, we get limit x tends to 0 1 by 1 minus x square root of this. We are left with this, and you know that this value is equal to 1. So, therefore, from that mu test we are getting this limiting value, that provided that we have taken that mu is equal to half, we are getting this limiting value is a finite number that exists finitely. So, therefore, we get that by that mu test improper integral I1 is convergent. So, by the mu test, by the mu test I1 is convergent. Next, we shall look at this improper integral I2. Okay. So, next we consider this I2. Next, consider I2. For this, look at this I2 is integral, oh sorry, this was c, not 0. This integral is from c to 1, and this integrand 1 upon square root of x into 1 minus x. So, this integrand is unbounded only at this upper limit. This c is greater than 0. Okay, c is greater than 0. So, therefore, the integrand is unbounded only at this upper limit 1, and for this we have to again go for this mu test, and what the mu value should be here. Well, in this case we take that when we go for this mu test, that limit of that x tends to 1 we shall consider. So, somehow you look at this factor, we are having 1 upon square root of 1 minus x. that we have to remove, so that limit x tends to 1 that we will able to determine. So, that is why we are considering again its I mean power of this factor, that 1 minus x is also half here. That is why same that mu value we can consider and that will work here. So, therefore, here also we take that mu is equal to half, and in this case we have to look at this limiting value, limit x tends to 1 and this b minus x, you remember b is here that 1 minus x whole to the power mu, that mu we are taking as half, and this multiplied with the function that 1 open x into 1 minus x its square root. So, therefore, this gets cancelled, that 1 minus x whole to the power half, and we are left with limit x tends to 1 open square root of x, and you know that its value will be equal to 1. So, this limiting value that is exists finitely, and also this is different from 0. So, therefore, from mu test we get that, well, of course, for this convergence case this need not be different from 0, but that remember this second bit of that mu test, there we are taking different from 0. Okay. So, if it is 0 also that works, only we need is that exist finitely, this limit should exist finitely. So, from the mu test again, so by the mu test I2 is convergent. We have got that both I1 and I2 are convergent, and hence the given integral, improper integral in this example is also convergent. So, this is what our conclusion here, that since both I1 and I2 are convergent, we get that the integral given in the example is also convergent. The integral of this example is also convergent. Well, we shall see more examples later on also. We shall use actually this mu test, it is very useful. Next, we shall consider another important kind of this improper, the test of convergence for improper integrals is the ratio test. Well, so this another important test of convergence is the ratio test, and this is also very useful, that also we will use. Well, for this ratio test also we shall consider that, well, means this name, from this name itself it suggests that we are considering a kind of ratio, means ratio of what? Well, we are given that integrand f, then we shall consider another suitable function g, and we take the ratio of f and g, and if they satisfy certain conditions, then we can tell about convergence of improper integral. So, what kind of functions, I mean f and g are, and what should be happen to their ratio, that we shall write down here. Well, let f and g be positive functions, means you understand, positive functions. Well, this one we are I mean looking into say type 1. So, therefore, I will say that this is first bit. Okay. Positive functions on this interval, positive functions means this f x is greater than 0 and g x is greater than 0 on this interval a to infinity. And in this case, if this limit, say here we are considering basically convergence of type 1 improper integral. So, therefore, we take this limit x tends to infinity f x by g x. We consider limit of this ratio f x by g x when this x, I mean we are taking x tends to infinity because we are considering here convergence of type 1 improper integral. If this ratio is equal to say, I mean this limiting value of this ratio, limiting value of this ratio, if this exists finitely, I mean say this is equal to L, that is a non-zero finite number. This L should be a non-zero finite number. L is a non-zero finite number, non-zero finite number. Then what happens to convergence of type 1 improper integral, integral from a to infinity this f x dx, and well in this case actually this improper integrals, these two improper integrals, they converge or diverge simultaneously. Let me write this, then we get that the improper integral a to infinity f x dx and improper integral a to infinity g x dx, they converge or diverge simultaneously. They converge or diverge simultaneously. So, meaning is that if the limiting value of this ratio is a non-zero finite number, then this improper integral will converge if this other improper integral is converge, if this one is diverge, the other one is diverge. So, converge or diverge simultaneously. If we know the convergence of one of them, then the convergence of the other also we can conclude, we will get. And similarly, if one of them is divergent, the other one is also divergent. This is the meaning of convergence, they converge or diverge simultaneously. Well, this is about type 1 improper integral we have considered. Similarly, the ratio test for type 2 improper integral we will have in the similar way. So, that type 2, for that type 2 improper integral, the ratio test we can write down in the similar fashion. Well, so again we consider that f and g be positive functions on this interval. So, here we consider f and g be positive functions on this interval A, B, A open and B is closed, means basically here we are considering that the functions f and g are, I mean they are unbounded at this point A, both of them, positive functions on this and A, B and A, B, a point of discontinuity of these two functions, A, B, a point of discontinuity of of f and g both. That means f and g both are unbounded at their positive functions, and we can say that they are positive and continuous functions. You may write that positive, I mean except at A, f and g I mean they are continuous everywhere, and A, B the only point, okay, be the only point of discontinuity of f and g both, only point of discontinuity in this interval, that I mean in this interval A, B, this A is the only point of discontinuity of A and B both. Then we will have the similar kind of test, that we consider the ratio of this same kind of ratio, that if limit here x tends to A is the only point where f and g have discontinuity or they are unbounded at this point. So, therefore, we look at limit x tends to A f x by g x. If the value of this ratio is equal to L, similarly a non-zero finite number, a non-zero finite number, then the same conclusion we will have, that type 2 improper integral we get here integral a to b f x dx. If this, then this improper integral and the type 2 integral a to b g x dx, they converge or diverge simultaneously. This and this converge or diverge simultaneously. Well, so this is about the ratio test for type 2 improper integral. Well, a similar kind of that also we get ratio test if the functions are unbounded or having discontinuity at the point B. So, these are some I mean test of convergence. So, recall that what are the test of convergence we have discussed today. So, we have first one, we have looked into that comparison test, and the second one is mu test, and the third one we have considered is the ratio test. Well, here I will just tell you another important, I mean this test, okay, that is also we do use actually, and that also I mean not difficult to check, I mean that criteria, that is called P test. Since I am talking about the all kind of test for convergence we are looking into. Here I will also tell you about this P test. Okay. Then I will give you a couple of examples using this comparison test and that P test that we will able to, I mean we solve some problems. Well, so here let us look at another one, that is called P test. So, this P test again I will consider for both type 1 improper integral and type 2 improper integral. So, for this P test let us take this B as an example kind of thing. I will just consider as an example here. So, look at this example. Here I am considering a type 1 improper integral, and here we shall see that when is this. So, I mean here I shall ask that, so that this type 1 improper integral a to infinity 1 open x to the power p dx, p is a real number, when is this convergent, this kind of improper integral, type 1 improper integral, that a to infinity 1 open x to the power p dx, p is a real number. So, depending on the values of p, for what values of p this type 1 improper integral is convergent, and for what values of p this improper integral is divergent. So, it depends on this value of p. Of course, here we consider is a is greater than 0. So, we have to show that this is convergent, this is convergent for p greater than 1 and it is divergent for p less than or equal to 1 and divergent for p less than or equal to 1. Here p is a real number, you keep in mind that p is a real number, p belongs to R, p is a real number. So, let us check this, I mean we will evaluate this integral and then verify this convergence or divergence of the improper integral, and we shall see that how it depends on the values of p for the convergence or divergence. While here we can look at, first we shall consider that p is equal to 1. First let p is equal to 1. First let us consider the value of p be equal to 1. So, in this case our integral will be like this, integral a to infinity 1 upon x dx. Well, what can you say about the convergence of this improper integral? For that, for checking the convergence of this, again we shall go back to our that definition for convergence, that we shall evaluate directly this limit b goes to infinity integral a to b 1 upon x dx. Okay, you know that this limit b goes to infinity, this value will be log x, and evaluate from 0 to b, and you are going to get this after taking this limit b goes to infinity, this is a to this is a to b. So, after simplifying you check that we get this value is equal to infinity, and hence for p equal to 1 the improper integral is divergent. So, a to infinity 1 upon x dx is divergent. This improper integral will diverge. Well, then next for other values of p, for p equal to 1 we have got the improper integral is divergent. Then for other values of p, that when p is different from 1, any real number that is different from 1, we shall look at into that case when p is different from 1. So, for this case, so therefore, we consider that next let p be different from 1, p is not equal to 1. In this case, what will happen to the limiting value of, again we shall look at this limiting value of this b goes to infinity integral a to b 1 upon x to the power p dx. We have to look at the value of this integration you find out, and then you take this limit b goes to infinity. So, what will be this limiting value? First of all you have to integrate this one. Well, limit b goes to infinity, what is the this integration, value of this integration, that you check that you get 1 upon 1 minus p x to the power 1 minus p, and you evaluate from a to b, and then you take limit b goes to infinity. So, this is just a simple calculation, and you will get the values be like this, that a to the power minus a to the power 1 minus p divided by 1 minus p for here for p greater than 1, and this is infinity if p less than 1. You can verify this. So, from here we can conclude that when p is greater than 1, we are getting a finite value of this limiting, and hence the improper integral we get in this example, that is convergent for this p greater than 1 and divergent for p less than 1. For p equal to 1 we have already discussed before, okay, and hence proved, okay, hence proved, okay, hence proved the result, in this example. So, this is about p test for type 1 improper integral. Then for type 2 improper integral, what will be the p test for type 2 improper integral? For type 2 improper integral, you know that this function, okay, let us consider that also as an example form. I will present. The integrand may be having unboundedness at the point, that lower limit a, or maybe upper limit that b. So, first we are considering this improper integral of type 2, is like this integral a to b dx x minus a whole to the power p, p real. So, when this is a type 2 improper integral, just you check, this is a type 2 improper integral, because it is unbounded at this lower limit a, only at this lower limit a. So, this is convergent, so that this integral converges for p less than 1 and diverges for p greater than or equal to 1. Just you compare with that p test for type 1 improper integral. For type 1 improper integral, it was convergent for p greater than 1 and it was divergent for p less than or equal to 1. So, it is just a reverse kind of thing, only at p equal to 1 both the improper integrals, that type 1 or type 2, both are divergent. So, this also similarly actually that we proceed, the proof is also similarly, just I can give you outline of the proof. One verifies like this, that outline I can give like this. So, here also we consider that separately, first we take that p is equal to 1. So, in this case the integral will be integral a to b dx x minus a, and directly again you can verify the divergence of this improper integral. I mean, you can check this limit of that epsilon. Just you recall, how do you test, I mean the definition of convergence of type 2 improper integral we had given. So, this is a type 2 improper integral and this integrand is unbounded at a. So, therefore, we have to consider this limit epsilon tends to 0 plus a plus epsilon to b dx x minus a. This is what you have to consider. We have to find out this integral and then we take limit epsilon tends to 0 plus. So, here you get this log of x minus a, well this integrand, and here we are having already this limit epsilon tends to 0 plus, and you evaluate a plus epsilon to b over here and then you check that you get this is infinity, and hence the given integration is divergent for p equal to 1. Okay. So, the given integral is divergent for p is equal to 1. Here in the similar fashion we consider that next we take p is different from 1, p is not equal to 1, and in this case also you have to consider that limiting value of epsilon tends to 0 plus integral a plus epsilon, the same limit to b, that dx x minus a whole to the power p. You find out this limiting value of this integral. Well, we get this value limit epsilon tends to 0 plus, again you check 1 open 1 minus p and 1 by x minus a whole to the power this p minus 1, that is what you will get, and take this range, I mean evaluate in this range, that a plus epsilon to b, evaluate this, and after simplification what we get, these values be, the values here we get like this. Well, the limiting value here we get is like this, 1 open 1 minus p 1 by b minus a whole to the power p minus 1 if this p is less than 1, and this is minus infinity if p is greater than 1. Well, and hence the result. This is how we prove, and hence the result. Hence the result. So, this is about that p test of type 2 improper integral when the integrand is unbounded at the lower limit a. So, similarly, what happens if we consider that type 2 improper integral and the integrand is unbounded at the upper limit b. So, that I can give you as an exercise kind of thing, that you check that. This is also similar way, the same thing, that similar way you can prove that. So, that integral a to b dx divided by this b minus x whole to the power p is convergent for p less than 1 and divergent for p greater than or equal to 1, that you can check. Well, these are some test that we basically use for the convergence of improper integrals. Well, so next there are many improper integrals, that important kind of improper integrals that we come across, and they are that very well known, gamma function and beta function, they are also improper integrals. Well, before I go to that, I had told you I will give you some example based on this ratio test and this p test. So, we will see a couple of examples based on this comparison test and ratio test, and then next we shall go for improper integrals, that gamma function and beta function. So, for this, look at this example. Well, here we shall consider the example is, well, I have told you that I will give an example on that is based on comparison test. So, examine the convergence of this improper integral 1 to infinity dx divided by x into square root of x square plus 1 say. So, for testing the convergence of this improper integral, here basically we shall use comparison test. So, the integrand here, the function is the integrand f x is 1 upon x into square root of x square plus 1. We shall use comparison test. Therefore, I have to choose another function g x suitably and then consider the ratio of f x by g x, okay, and then the limit x tends to infinity, of course. So, here I shall select g be like this, consider g x is equal to 1 upon x square. Well, then you take that limiting value, I have told you limit x tends to infinity, this is type 1 improper integral. Therefore, we are taking this limit x tends to infinity f x by g x. Well, by substituting these functions here, that we get limit x tends to infinity x by square root of x square plus 1, and after simplification that you can divide by this x here and take inside that, you get this limiting value, that is easy to obtain, that value is equal to 1. And hence, by the comparison test, that L, this is a non-zero finite number, that we get the integral, okay, then by the ratio test, the integral f x dx, that 1 to infinity f x dx and integral 1 to infinity g x dx, they converge or diverge simultaneously, converge or diverge simultaneously. So, for this, well, this g, you know, that I mean we will able to evaluate this improper integral, that integral 1 to infinity, that g x is 1 upon x square dx, that easily you can verify the convergence or divergence of this improper integral. You can also evaluate by direct method, or you can also use your that p test also. Well, look at this, what I am saying is, now we shall consider the, I mean this improper integral, that 1 to infinity g x dx is 1 to infinity 1 by x square dx. So, what can you say about convergence of this improper integral, that integral 1 to infinity 1 by x square dx. Well, I think we have already seen earlier this function, and also otherwise also you can apply your p test. Okay. So, you can also apply the p test and say that this is convergent. Okay. So, directly either you evaluate this improper integral, or you can also go for p tests. So, here you see that this is type 1 improper integral, and that value of p is also that is greater than 1. Okay. So, therefore, this is convergent. This is convergent by p test, or by direct method also you can check, or check by direct method. So, since it is convergent and hence this integral, given integral is also therefore convergent. Okay. Hence, the given integral is convergent by ratio test. Well, this is how we apply this ratio test and verify convergence of the improper integral. Well, let us consider another example. Here I will ask you to test the convergence of this type 2 improper integral, say 0 to pi sin x by x cube dx. So, again we shall use this ratio test and verify the convergence of this type 2 improper integral. By some other method also one can verify, but here we are taking example where we use this ratio test. So, therefore, in this case we take this function integrand f x, that is sin x by x cube, and then g x I will take. So, consider this same of course, the same g x in the previous example that I have considered, that same function actually it works here. G x I have taken 1 by x square. So, now look at this integrand is unbounded at the lower limit 0. Therefore, we have to take this limiting, and similarly this function g x is also unbounded at this lower limit 0 only. So, therefore, we consider this limit x tends to 0 and f x by g x, this ratio. So, now you verify this is equal to 1 here in this case, that limit x tends to 0, we are getting this sin x by x, and that is equal to 1 we get. So, this is a non-zero finite number here, this limit is a non-zero and that is finite, exists finitely and non-zero. Therefore, from the ratio test they converge or diverge simultaneously, and already we have seen that this integral, that since integral g x, that you can verify that from this again by the p test also, that 0 to pi g x dx. In the previous example we have look at the integrand was 1 upon x square, but limit was from 1 to infinity, and here this limiting is from 0 to pi. Okay, this limiting is 0 to pi. So, this is a type 2 improper integral, I mean integral we are having 0 to pi dx by x square. Using the p test also we can conclude whether this is convergent or divergent directly by the p test, or otherwise you can also use that definition of convergence by the direct method also you can compute. Okay. So, suppose we shall consider the p test. So, you know that by this p test what happens to this? It is divergent. So, this is divergent by p test, and hence the given integral, this integral is also divergent. Okay. Hence, the given integral is divergent by ratio test, by the ratio test, because from the ratio test the given integral and integral g x dx they converge or diverge simultaneously. Well, so today we discussed all about the test of convergence of improper integrals, that we have seen various kind of test of convergence. So, just you recall once again that comparison test, mu test, then we have come to this ratio test, p test. So, applying these tests we can verify convergence and divergence of some improper integrals, and next class we shall discuss about those two very important kind of improper integrals, that is basically we say gamma function and beta function, and that is all for today.